Thank you for being here for the second class of Dr. Noemi. So Noemi, you have the floor.
Thank you, Georgie. Hello, everyone. Thanks for coming back after lunch and not taking a nap. I'm going to try to keep you entertained so that you don't feel tempted to close your eyes. And today we are going to go with rock and roll and icy bodies. That is what I like the most. And I'm going to introduce also JWST, its capacities, and why I think it's going to be key for the study of these small bodies. So I'm going to take it more or less where we left it yesterday. Yesterday we were talking how the ices form on the clouds and they end up in the disk. And I mean, after a big parenthesis, around a star, you can have a solar system like the one that we know, or different. I mean, the one that we know have very specific characteristics. That is what we try to explain with our observations. So this is the kind of solar system that we have with 8 planets, some of them that have objects that form closer to the sun than the H2O snow line are going to be rich in silicates, in sea ice, and in chondrules, and poor, of course, on ices, and they will have traces of water in just because of the intermix of the water with the silicates at some points, but not ice. Then, we have Jupiter, Saturn, Uranus, and Neptune, and between Mars and Jupiter we have the asteroids belt with different regions, and that has different kind of populations of objects that are supposed to come even from different origin, but we will see that later on. Then at some point there is the snow line of the CO2, the carbon dioxide, that is the next one in the sublimation temperature, and that adds a vital component to any chemistry that can happen in the system, that is the carbon. And we have different objects that form beyond that. So also, as we will see a little bit later, there is objects that formed in the outer parts and that migrate at some point or are scattered in, so they may have some indications of the CO2 and H2O, even if they are in the inner region. And we will have some that formed inside and are scattered out, and different kind of happy and funny events. So for the snow lines, this is the distance to the sun on the horizontal axis, and you have the temperature on the vertical axis. And you see how it goes from the hotter regions, from metal-rich materials to silicates and rocky material, water ice, CO2 we were saying goes after, then ammonia ice, and some other ices that are in the middle. And that is going to shape what we see today on the surface and on the interior of some of these objects, if we can study them with radar or with other similar techniques. This is a little bit of information on the typical temperatures of sublimation of these ices, and on the abundance that is measured on the comets, for example. You know that I like to study the icy small bodies, the trans-Neptunian objects, but for a long time the only indication on which could be the composition of these objects came to us from the study of the comets, because we knew the comets had an origin and on the outer regions, and they are rich on ices, so whatever we observe on these comets is what we think is on the surface, or at least close to the surface on these other objects. This is a little bit of rock and roll. I'm not going into detail because it could take too much time, and because I'm not a dynamicist. But for those that don't know, and also because this is not the only model to explain the origin of the solar system. I know it's not very popular here. But it's kind of the most standard, the most assumed. It has things that do not explain what we see today, and that's why there is space for other models that may explain those things and may not explain others. It's very difficult in science to have the final answer to a question. So there are always open threads that you can pull out and may take you further than others. But what is, I think, important here, the evolution goes from top to bottom, and is to see how this rocky material that initially forms inside and the icy material that initially forms outside is scattered around is pushed also inside and then pushed outside. And so what you see at the end, if you study what is on the surface of these bodies at the end, it may not reflect the snow lines or the temperatures of the location where you are studying them at the present time. It may be a reflection of what the region where they formed and what was available in the disk and in the cloud where they formed. So that's very important always to try to find connections with the dynamical models, because it will help you explain what you observe, and it's also important for the modelers to know what is observed, to use them as input or constraints for their models. So what is left after all this rock and roll? I love this illustration. It comes from Eleanor Lutz, that has a lot of things in her web page that are amazing. And what she is representing here is 18,000 small bodies. Of course, these are not all of them, but this is everything that has more than 10 kilometers in diameter, measured or estimated. And it contains about 10,000 asteroids that are represented by dots, and 8,000 randomized objects. We don't know the size exactly, and they are represented by dashes. The different colors represent different populations. So, for example, you can see here, okay, let's take this. If we go from the sun, so we have some objects here that, of course, they are near-Earth asteroids, okay, all the yellow ones here. Then you have the inner, central, and outer main belt, that is all of this region here. Then you have these clouds, the clear pink one, that are in resonance with Jupiter, and that are the Hildas. You have the two clouds of Trojans that go before and after Jupiter. And then you have outside Jupiter all of these objects that are the trans-Neptunian objects. Of this population of trans-Neptunian objects, that includes, of course, the icy dwarf planets, there is another population that I will typically refer to them both under TNOs, but there is another population that is very interesting and is different because it's a transitional population. As I was mentioning, we know that the short period comets, the Jupiter family comets, they come from the trans-Neptunian belt. But they do that not directly. They have an epoch in a transitional population that is called the Centaurs. And this population allows us to see trans-Neptunian objects that are put closer to the sun, so they suffer different physical process. It's changing automatically. They suffer different processes, like is the sublimation and formation of dust mantles. We will see that later. This is a good example of the observation of one of these centaurs that turned into a comet of the Jupiter family and was pulled, and its orbit took it to collide and to impact Jupiter. Okay. So let me talk to you a little bit, for those that are observers, of the observational challenges of studying the icy small bodies in the solar system. It's not only that we don't know so many, we are in the small numbers, but it's also that it's not the same as detecting one object than extracting information that is useful for you. For that you need to do observations, and if you want surface composition, you will see that later, it's better to do spectroscopy. So, for example, if we take an object in the 30-kilometer scale, if it is a near-Earth asteroid, like Ganymede, with this semi-major axis and perihelion, like around 2.4 and 1.2, then an albedo of 17%, that is typical for these objects. You can, if it would have a visual magnitude of 12, and you could study it pretty well with 1 meter telescope. If you move from the near-Earth asteroid population to the inner main belt, like this object, for example, in the same scale of size, and this would be the orbital parameters, well, the albedo of this object is around 6%, that is typical for asteroids also. And the magnitude, the visual magnitude, will be now 17%, which means that you need a 3-meter telescopes. If you jump to the centers or the TNOs populations in the same scale, you will need 5 to 10 meter telescopes, even if you have something with a visible albedo of 23%, that is typical of TNOs, and is way larger than 6%. But you need very large telescopes to really extract meaningful information. And it's better even if you go to a space telescope as the HST. Another challenge is that I was mentioning before, one parameter to know how bright an object is for us is the amount of light that they reflect from the light that they receive from the sun. We are not studying objects that emit their own light. They are reflecting a standard candle, that is the sun. So, depending on the visible albedo, you may have an object that, two objects that look the same brightness for us, but if they had a small albedo, then they would have a larger size so that we can see them so bright. And if they had a higher albedo, then they would be smaller. So if we don't have the information on the geometric albedo, it's very difficult to really know which is the size of an object just from how bright we see them. So that we can do estimations from the absolute magnitude, but it's always going to be an estimation that needs to assume some kind of albedo. Another observational challenge is when you go, for example, to the longest wavelengths, when you want to extract this thermal information that tells you how bright an object is. There are not so many instrumentation. There is not so many instrumentation available. There were two very good space telescopes like Spitzer and the Herschel Space Observatory that could do that. But the thermal light from these cold objects has a peak at very long wavelengths. So, for example, you can see here the predictions for TNOs. Depending on the size, the maximum peak moves at different, depending on the size and the albedo, it moves at different, the size is here, and this is the distance, from 20 astronomical units to 100 astronomical units. So it moves to the very long wavelengths. And it requires a lot of a very good thermal camera to be able to take the full thermal emission and using the visible, the information in the visible, be able to correct and to extract this information about the thermal emission and behavior. So, icy objects. What do we have when we talk about TNOs? I love this this representation. It goes only to 2020, but it's very illustrative of how many objects we know at this point. We have about 3,000 TNOs and a little bit more than 1,000 centers discovered, not characterized. And you can see that, I mean, this is all the minor planets, the numbered ones, the ones that we know the orbit better, the comets here. There is always an increase in these curves, depending on the instrumentation. Probably there was some survey going on there and some different interests that sparked the detection of these objects. For TNOs, we have known one for a very long time, one all this way here, that was Pluto. And then this was the first discovery of another one in the modern era, and from here it starts growing up, just from 1992. And that is why we are still at this amount of objects that will change probably with the surveys that are designed, but at this point we are stuck at that number. We talked before about how to make, important is to make connections between where objects formed and where they are and everything. There are different dynamical populations in the TNOs, and some of them are going to be very diagnostic to validate the models for the formation of the solar system. What you see here is that most of the TNOs are beyond 40 astronomical units. This is eccentricity and this is inclination. There is a large population that has low eccentricity and is stuck between 40 and 50, that are the classical TNOs. And in this population, there is one that is very interesting, that is the low inclination ones, the ones that were not really excited dynamically. And this is a population that is thought to have formed in the outer regions of the disk and have been pushed out but kept in the plane. So they are the ones that are going to be richer really in volatiles and in ices. Then these are the centaurs, the ones that come closer. And then there is a number of excited populations that are the resonant ones in these dashed lines, and the scattering objects and the detached objects. The difference between scattering and detached is that the scattering are still under the influence of the giant planets of Neptune, and they are being scattered out or up, and the detached, they are already out of this influence, but they have been really excited. So studying these different populations, we can try to guess things about how the disk was, where they formed. The size range for the TNOs, the ones that are discovered up to now, they go from tens of kilometers to about 2,000 kilometers, and probably the lack of smaller objects is a question of an observational bias. There are different ways to estimate smaller ones, and one way has been using observations of new horizons of the craters on Pluto and on Charon, so that you can know the smaller populations. But the story gets more complicated, not only because of the dynamics of the origin, but also because how the surface of these objects evolve. We are trying to guess what they had on the surface, where they formed, to see how was the disk shaped. But from that moment to now, even if they are the less processed objects, the surface materials are processed in different ways. So one of the things that we take always into account is the capacity of each of these objects to retain the ices on the surface, depending on the temperature, or how many times they approach the sun and everything. So, of course, this model in particular is very simplistic, but it explains some things. Basically, it explains that none of them will have volatiles, only the largest ones. But I mean, the two variables, the main variables here are the diameter of the object, that tells you the gravitational force that is pulling those molecules that sublimate back to the surface, and then the temperature, because the temperature is going to trigger sublimation and is also going to provide some energy for those molecules to escape. So the competition between those two processes, if you approach it with the Jeans escape, then it tells you that every object on the left of these lines is going to be depleted on these original volatiles, and everyone outside of this could have a big amount of these original volatiles. But as I mentioned, this is very simplistic, and there are a lot of things that it doesn't take into account. We don't know exactly, of these objects, of many of them, we don't know the inclination of the axis, for example. We don't know if the surface is homogeneous or is heterogeneous, and it may be hotter in some regions and colder in another ones. We don't know really the shape of the body. These and other things are going to influence. More complications to this, more ways for the surface to evolve. So one way is irradiation. Whatever it had originally, it has been influenced by energy deposited by micrometeorites bombardment that sublimates small amounts of material around the area, then by solar wind ion irradiation that erodes the surface and also triggers transformation of the molecules, high energy irradiation from outside, cosmic rays, anything, all of that is affecting at the surface. And the main way of space weathering and the irradiation for these molecules that are ices is not the iron as it is on asteroids, it's the hydrogen. The energy breaks the bonds with the hydrogen and frees some hydrogen and some other molecules that are able to chemically aggregate again and transform into more and more complicated molecules. These are the final stages that we are always looking for. These are combinations of carbon, hydrogen, and oxygen, and it can happen in the way of rings that are aromatic complex organics, or in the shape of chains that are the aliphatic complex organics. That's something that we have always been looking for on the surface of these objects. Another way of evolution of the surface, we already mentioned this when we talk about centaurs. If you have a surface that has silicates, smaller and bigger, and that has ices, that would be the yellow material here, and you start heating it up, then the ices are going to sublimate, so the part of it is going to escape, part of it will redeposit on the surface, on the cooler areas, and you have exposure of the larger chunks of silicates, and you have some smaller silicates that are thrown up, and that part of it will come back, but part of it will also be lost. So you end up from a surface rich on ices, you will end up on a surface rich of dust mantles. That is what we observe when we observe a comet. When we observe an inactive comet, and we can observe the surface, you see surfaces that are really depleted on ices. And that's what we think happens with centaurs. Another way of altering the surface is the possibility of atmosphere retention. If you have an object that is big enough to keep some of these ices when they are sublimated, so they go to the atmosphere, part of it is so energetic that it passes the exosphere and is able to escape, but part of it will recondensate on the cooler areas. And this is a process that if it keeps happening, it will create big gradients on the temperature and on the composition of the surface, because the hotter areas will keep absorbing more light and will have faster and faster sublimation. And the cooler areas will be replenished continuously by more and more ice. So it's something that can turn surfaces kind of homogeneous into a very heterogeneous surfaces. These atmospheres may be local or maybe global atmospheres, depending on the amount of ices available and on the size of the object. Then there is cryovolcanism, that can sound very exotic. Cold volcanoes that do not emit lava, hot lava, they emit icy fluids, you know? And even if it is looks very exotic, it has been proposed because of what has been detected, for example, for Europa, that is one icy satellite. And it has also been proposed for some smaller TNOs because of what we observe on the surface. On the TNOs, of course, you don't expect to have an actual thick ocean below the surface, but what it happens is that if the inner part of the TNO has enough aluminium and enough temperature, then you can have, and if the content of this ice has some nitrogen salts, is like H2O and H4, for example, then at the temperatures, the water would be ice, but this component would be fluid. So it can escape through the cracks and it can deposit on the surface. So we have always looked for NH4 materials on the surface of TNOs as an indication of possible cryovolcanism. So all of this complicates a clear path to interpret what we see on the surface of these objects now and what it was when they formed. As a reminder, because I'm going to start talking about what we expect to find on, or what we find on the surface of the TNOs, these are molecules that we mentioned yesterday that are typical on disks. These are the simplest ones. Remember that we talked about water, methane, carbon monoxide, carbon dioxide, nitrogen, neutral nitrogen, and also methanol. And these are the simpler molecular ices, and these are the most common that we look for on the surface of TNOs. So what do we observe? This is a representation of the results of a large program that worked with the Herschel Observatory. Remember that I told you that the albedo is an important component to really understand how big these objects are and how much of the light they absorb or reflect. So this is a collection of about 170 TNOs that this program, TNOs are cool observed, and they have a determination of the geometric albedo that is here in the visible. Some of them in the infrared, but you can pass from one to the other. And if you have this and you have the absolute magnitude, then you have the size. So we can have a good measurement of the size of these objects. And here what we have is the visible color. That is, photometry is always easier than spectroscopy for faint objects. Easier, I mean that you get to observe more objects that you can observe with spectroscopy. So you can reach larger numbers when you do photometry. And what we have been collecting for years and years shows a large disparity in the color on the surface. So a 0% of the slope in the visible tells you that the color of this object is like the solar colors. So if you would be able to do a spectrum from 0.5 to 1.2, you would have a neutral, a totally horizontal line. So some objects have this color, but not so many. The more you go up, it's telling you that the object is redder, what means that it's brighter in the reddest part of the spectrum. So you would have like this way visible continuum for the spectrum, brighter in the longest wavelengths. And this 50% of the slope is really a large dispersion in colors. The fact that the colors are different, because all these complex organics materials that we have mentioned before, they are typically red. So we have not been able to detect complex organics in the visible or infrared, but we always took the fact that they are very red as an indication that they have a lot of complex organics. What means that originally they had CO and CO2 and all of this fun samba, you know? What happens with the albedo? So most of these objects have an albedo below 40%, and actually the most common are below 25%. You can see that we have a good representation of sizes here, from like 5 kilometers to even the largest ones that are Pluto, Iris, Haumea, Makemake, the only official dwarf planets in the solar system. So most of them have an albedo of 25% and below. Only the brightest ones are the largest ones. You don't have large objects that are dark. We take as an indication that they retain a lot of volatiles that are brighter, because the complex organics are very dark. Then when we see the colors here, you have all of different colors here, and you still have different sizes. Even for small sizes, you have all the colors. For medium sizes, you have almost all the colors. And if you can draw lines also in this way. The only special guys, again, are the dwarf planets and a couple of objects that are large enough also. So there is diversity here. The difficult part up to now was to interpret this diversity in terms of composition, because we have indications, but we don't have real detections. Let's see what we have. Okay, this is a different representation of the same thing. You have the albedo here, you have the color here, and the size of the dot is proportional to the size of the object. So again, you can see in every single color objects larger and smaller, even on the neutral ones, what means that there is not a clear correlation between size, color, and albedo. Okay, so what do we see when we get to do spectroscopy? Spectroscopy in the visible is easier than the spectroscopy in the near infrared. These are all visible spectra from 0.5 to 0.9, and they show what we were seeing with the colors, different slopes of the spectrum. So again, we take this as an indication that the ices are mixed with some materials that can be complex organics, or even could be silicates, because the silicates are slightly red. but there are not absorption bands that we can really trace to elements on the surface. What happens when we add the near infrared? So the first thing that happens is noise. The infrared spectra are noisier always, and they have these gaps here that are due to our atmosphere. The solid lines here are not data. These are models fit to the spectrum. The spectrum is the noisy thing here. And this is not a criticism to anything, because this may be my own spectra. Actually, some of them are. It's just that we work with the instrumentation that is available and we exchange information from there. Which is the information that we have here, basically? The color, again, can be different from very neutral to reddish to red. But there are also these absorptions here that we see in all these four objects. These absorptions here are interpreted using laboratory data as water ice. Water ice has two strong absorptions in these wavelengths, one at 1.5 and the other at 2.0. That is where these are. And even if the water ice is in crystalline state and not in amorphous state, then we have this band here. So we can already say, okay, we have detections of water ice and we have detection of crystalline water ice. Those are two things that we have added to the equation. What happens when we go for the dwarf planets? The ones that were really special, very bright and very large. The spectrum is totally different from those others. And we kind of were seeing that in the albedo and in the color. So these are three of them, Pluto in black, Makemake in yellow or orange, and Iris in red. These spectra are practically the same. If it goes for which detections we have a small band here that is deeper here, we have this band in the three of them, this band, complex bands here, a lot of them in the visible that we didn't have in the other. All of these bands come from the same material. So we have a lot of bands, but it's just one other material. In this case, it's methane ice. Is very active, and even in the visible you can see a lot of bands there. The fourth dwarf planet, however, is totally different. This is only visible, this goes to 0.9. So if you go here to 0.9, that would be here, you would have a totally neutral, fully neutral, and featureless spectrum. And what does this correspond in the near infrared? To the 1.5 and 2.0 absorption bands, but really deep and really well defined, even for an object observed with ground-based telescope. So this one is Haumea, that is a dwarf planet, and when we feed models like the one that is overplotted here in gray, we can extract information of the surface composition. In this case, this object has a limit of 8% of contaminants on the ice. It has to be 92% water ice and maybe 8% of other things. Okay, so this and some objects related to it are the only ones that have this composition. What do I mean when I say models? Models is the way that we have to study to get the recipe for the surface of these bodies. And what do these models do? They study the albedo of an object, the light that you receive, after the light passes through different scattering and reflection processes in multi-particle surfaces. In particular, Skouratov, what does is it approximates all of these changes in direction. In each of these surfaces, there is not only a change in direction, because some of the light goes through, so there is reflection and there is absorption. And it happens multiple times. Comes in, and at the end you get something out, in and out. So it approximates it by multiple slabs where you can account for all of these processes. This is good enough for the spectra that we have, and for objects that we observe them always like they are so far away that we observe them always like at phase 0, we call it. That is when the light comes perpendicular to the surface and comes out in the same direction. We don't know if you have a flyby that is going around the surface, then you will have different angles of incidence and emission, but not for these bodies. So this approximation is good enough. There is another model with different variations, that is Hapke, and it gets a little bit more complicated because it uses other parameters to try to reproduce. It's way better when you have a flyby, for example, but it's not really needed for these subjects with the data that we had up to now. Both of them have provided good information on the surface composition indistinctly one of the other. How do this work? So we make use of the optical constants of each of these material obtained in the laboratory. The optical constants have two components. One is, it tells you about the reflection, and the other tells you about the absorption, and it's going to be the one responsible for all these bands. And if you take into account those optical constants, then those are the inputs for your models. And at the end, imagine we have something like the noisy thing that is here in the back, that would be the spectrum. And we were able to model this spectrum considering all of these materials. Which are the other variables in this? So you have the optical constants, but you can have also to consider the particle size, because the behavior of the light is going to be different in the particle and outside of the particle while it travels to the next particle. So depending how big or small the particle is, the scattering is going to be different. And it takes into account the relative ratio of all of these ingredients here. So we have pure methane, pure water ice, these that we call tholins. These are the complex organic molecules, the COMs, that, as I said, they are red, they don't have absorptions, but they provide the red color to the surface, this deep slope here. And then graphite is another step in the irradiation of this material, that is just a black coal on the surface that lowers the albedo but doesn't affect the shape or the bands. With all of this, we put it in our machine, modest generator, and we get the geometrical albedo as a function of wavelength, so all of this spectrum that we have here. And this is especially powerful if you have the value of the albedo in the visible at 0.55, because it's not the same to have a surface that reflects 90% of the light, as is Haumea, or another one that reflects 10%. So we have to take that into account. Another thing that we have to consider when we model the spectra is how the different materials are mixed. And there are three kind of materials that kind of mixtures that we typically consider. One is what we call aerial. Imagine like a chessboard. You can, if you take a piece, you can always pick to take a piece of the white material or of the black material. So you can separate the elements on the surface. And that is what is called an aerial mixer. That is a linear combination of the reflectance of the different components, 2, 3, 4, in proportion with the amount of them in the surface. But then there is also a salt and pepper mixer. It's like the sand on the beach. It has different components, and you cannot separate the smallest particle there. If you take a spoon of it, you will always have all of them. So you have to consider in every single smaller unit, you have to consider all the materials. That's a salt and pepper. Then there is the possibility of inclusions, that imagine that you had a big chunk of ice and you had very small particles, not comparable with the size of the wavelength of another material. Then it's going to produce a different kind of scattering. And this is what we call inclusions. These are the three basic, but you can complicate the picture as much as you want. The problem with complicating things is that you need to have good estimations of the different parameters that you're going to use, and that is not always possible. So sometimes, and in this it works, and in most of the things in life, the simplest, when you don't have good estimations, when you don't have a full knowledge, it's better to go for the simplest explanation. So, and okay, another problem added to all of this analysis is the degeneracy of the solutions. This is particularly strong when you don't have many absorption bands. I mean, if you have that spectrum with a lot of methane, you have a lot of constraints in your model because you have to fit every single band. But if you only have a continuum and maybe one band, or only a continuum, then the degeneracy of the solution is going to be larger. You reduce it with the albedo, but not always. And this is another example of a surface here with one only band at 2 microns that could be water ice. So we started with this collection of materials. This is the same spectrum in a different scale. And what we got at the end was there is a collection of models where we extract the 18 best ones that fit this spectrum with the same statistical significance. I mean, you can have as many as you want, making your space of input parameters smaller, but at least with this 18, we could kind of represent very good the spectrum with the albedo taken into account. This shaded region is where these different models would cross. And this represents the degeneracy in the concentration of each of the materials and in the size of the molecules. Some elements, some parameters are better constrained, in particular the water ice, because you have a band. But when you don't have bands, as silicates and complex organics, you will have more dispersion in your solutions. So, what have we done in these 30 years with about 30 good spectra that we have of TNOs and that we have been able to model? Basically, for 50% of our sample, do not show any detection, what means that the models would not be really very well constrained. So there are these kind of objects where you have a slope that is the same as having photometry. Then there is 50% of objects where we have absorptions at 1.5 and 2.0 that has been interpreted up to now as water ice. And tomorrow we will talk more about that, because I'm not so sure about that anymore. So these detections at 1.5 and 2.0 are the most common ones, and they have been also studied with photometry. If you make a strategic photometry from HST that allows you to go to fainter objects, like you take photometry in the continuum at these deepest points, then you can kind of check if the spectrum goes down here or the spectrum goes up here. And that is only 50% of the sample. Of this sample of like 30 or 40 TNOs, we only have 3 of them that are methane rich. The 3 dwarf planets, Pluto, Eris, and Makemake, the only ones. And of these, there are only 10 that are water ice dominated, as Haumea is the dwarf planets that I showed, and the other objects that are water ice rich, they are dynamically related to this body, to Haumea, up to the point that the hypothesis says that this is a collisional family. So they all would come from the same parent body, and that's why they are water ice rich. So this means that these compositions, methane rich and water ice dominated, are not common in the Trans-Neptunian belt. There are always going to be other materials mixed with the ices. What is not surprising, because the most abundant material in the disks is silicates. And it's also not surprising because we know that these objects have been processed through irradiation for a long time. So if they had some ices, they may have now crushed this of very evolved complex material. So let's go now for web. How much time do I have? 10 minutes? Okay, so let me run a little bit because I want to show the good, or if not, I can do that tomorrow, don't worry. So this is web, and well, I'm related to it because I'm co-I of a Guaranteed Time Observation program and PI of another program that is a large one, so I have access to 170 hours of study of TNOs, just TNOs and femtors. It was launched in 2021, on December, and it was built by NASA, but also by ESA and the Canadian Space Agency. And actually, the instrument that ESA provided is the infrared spectrometer that I'm using, near spec, as high as a 3-stories building, and the primary mirror is 6.5 meters. So it's a very large mirror. You cannot launch something like that with a 1-segment mirror, so it was composed of 18 segments, and it had to be, okay, this is where it is now. It's orbiting at the second Lagrangian point, so that is far enough to be protected of the more dirty area around the low Earth objects, and also so that it can be protected from the sun, because if we're going to go for near infrared, you want it to be really cold. So if you want to compare it with where Hubble is, so Hubble orbits at 350 miles, the moon at 240,000 miles, and JWST is almost at 1 million miles. So really far away. This is another characteristic of Webb, and is that it doesn't need a cryogenic system to keep it cold. It's doing it with a protection. These panels here, that is like a thin aluminum paper or sheet. Actually, it's 1, 2, 3, 4, 5. So if the sunlight impacts here, where the temperature is 358 kelvins, the heat is disseminated, is diffused, and you get very small heat in here, keeping this part of the telescope where all the instruments are and where the mirrors are at 40 Kelvin. So this difference is huge, but is what is needed to be able to observe in the infrared. And now we know that it's working. When I first gave these talks, it was all like, we hope it works. So I was telling you before how you cannot launch the telescope as is going now, as it is now. It's an origami telescope. You have to put it in a very small capsule, so fold it up to 5.5 meters wide inside this capsule. So it was also all hopes that the process to unfold is going to work. So if you want to see how it was really, you can see here 3 segments of the telescope. You can see here the sheets for the heat prevention, and this is the size of a person, so you can see the scale. This was how it was folded and launched to space. 30 minutes after launch, the solar panels were unfolded, and it happened. We could see that very good. So on its way, there were a number of processes that had to happen until it was operative, and it was a 1-month nerve-wracking month, all January, where I had on my fridge this list of tasks that were happening every time, but everything worked nominally. So we were checking it, got it. It really worked incredibly. It was a huge work from the operations group and the design group. So now it's orbiting there, and what is giving us Webb? So this is the size of the mirror, and it's giving us, it's not only about the spatial resolution. Hubble had a great spatial resolution, you see here, but it's about the fact that it observes in the near infrared and that is very sensitive. So way sensitive than Spitzer, that was the other near-infrared telescope. This is the resolution. 0.64 is the regular one at 20 microns. At 2 microns you can reach even better resolution than for Hubble. But very, very better than the one that you could get from Spitzer. This is the wavelength coverage from Spitzer, JWST, and from Hubble, and this is the ultraviolet to the infrared, the thermic infrared. So JWST goes up to 30 microns. This is how the field of view of the different instruments is positioned. So you have a near-infrared spectrometer, near-infrared camera, infrared spectrometer and imager, and then you have this other spectrometer that is not really, is better for exoplanets, not for our field. And then this is the guidance and system, The good thing, it cannot point everywhere at every time, because then it would point to the sun and it would heat up. But because it's orbiting, then you get a full view of the sky twice a year. So you have full coverage of the sky twice a year. This shows how versatile the instruments are. This is the coverage in wavelength range. These are all the modes for spectroscopy and all the modes for imaging. Coronagraphy, we mentioned this yesterday, for the detection of these disks around formal house. And you have IFU for spectroscopy, that is the one that is optimum for solar system, and then some multi-object and some single slit that are better for galaxies, stars, and crowded fields. This is the sensitivity, so photometry for JWST, way better than any other thing used up to now. This is for spectroscopy with near spec and with MIRI, way better than anything up to now. And MIRI is way better than the Spitzer, that is the only one comparable at this wavelength range. Then I think I'm going to talk about this tomorrow probably. That is how we are going to use the wave for the compositional study of the icy objects. Is it okay, Georgie? Yeah, okay, I mean it's like 5 slides, no more. Okay, so I go. This is a representation with optical constants of the reflectance of materials like water, methane, silicates, methanol, organics, and CO2. Up to 5 microns, that is where near spec goes. And DISCO is the name of the large program that I have been awarding and I'm leading. So we did this kind of representations. Every line here is different size for the different materials that we were expecting to find, so that we can try to convince the panels of all the diversity that we were hoping to detect on the surface of these objects. These are simulations of fluxes from different kind of objects that we had already modeled with visible and near infrared. For example, we have here Pluto with a lot of methane. We have here Eris, another of the dwarf planets. This is Caronte, the binary with Pluto. This is Sedna, a large object with, we thought it had a lot of nitrogen and maybe ethane. And this is the limits for the different modes of near spec. Near spec has low resolution, mid resolution, and high resolution. So high is better, but only the lines here that are above these lines are achievable. Everything that crosses below, you are not sensitive enough to observe it. So for example, if you want to go for an object like Sedna, you would lose all of this information here if you were, no, I mean all of this information here if you were with high resolution. So we use this to predict that we could observe it with mid resolution, but better with lower resolution in this part if we wanted to really go up to 5 microns. And these are the really large ones. What happens with the regular size ones? So you have here the high resolution. Most of them are below this in this area. So you cannot try to do them with high resolution, but even with medium resolution. So the best option for the regular size TNOs and Centaurs is the low resolution. And I mean it's low, but it's even better than the one that we get on ground-based spectroscopy. And also we saw before with the reflectances that the bands that we are aiming to find are very broad. So we were sure that we could do it. Another thing to show this was, okay, let's take the models that we have. I have been modeling TNOs for 20 years. So let's take these models, extend them to 5 microns, and with the exposure time calculator, let's reproduce the signal to noise that we could get with the kind of observation that we're telling them that we are doing. So these lines here are the signal to noise. You can see as all of these objects had very good signal to noise on all this lower part of the spectrum. And it had even very good signal to noise to detect the CO2 that is represented here with the resolution, so that it tells you that you have really enough points to try to study the shape of this band. And it's not only the CO2. We can see water ice here. We can see other materials here that are solids that give the red color there. We have the big 3 micron absorption due to NH, due to water ice. That we thought this was our prediction of what we were going to see with wave. And I want to add this to my presentation tomorrow so that you can compare with what we are seeing. Then these are other different models, just zooming out at 3 microns to 4.5, and this was to tell them that apart from all of these absorptions, we could try to study, for example, the nature of the 3.3 micron band due to complex organics, if we were seeing aliphatic or aromatic, of which kind of complex organic. Remember that I told you yesterday there is a lot of interest in first detections, because none of these materials had been detected on TNOs before. But we also want to know the nature of these, if they are crystalline, if they are amorphous, if they are mixed with other materials. And we can do that if we have enough detail on the shape of these bands. But also we could detect methanol, for example, here. We could detect N2, we could detect HCN here. All of these products on the different stages that we saw yesterday on the formation of ices in the interstellar medium. This is just the simulation for the Haumea family, the one that is rich in water ice. And this was something that was giving us a lot of hope on what we would see. Each single point here is an object, and this was made with photometry using Spitzer. Okay? So this is about 100 TNOs. Every single object that is here below this line means that it's absorbing at 3.6. 3.6 is where the broad band of water and organics occurs. So all of these objects were supposed to have water ice or complex organics on the surface. And here, this is an absorption at 4.5. That could be indicative of, for example, water ice also, but it's also where you can separate complex organics from water ice and from silicates. So only these ones had an absorption there, what was telling us that combining observations at these wavelengths, that is what Webb adds up, Webb gives you from 2.2 to 5, where we had never observed before, we would have enough diversity as the one that is reproduced here. The points are real values, and the shaded areas correspond to different materials like complex organics, methane, methanol, this is CO2, and N2, this is water ice. But this also shows some limitations that we will see when we compare tomorrow with real data. For example, we almost don't have objects here where CO2, CO, and N2 happens. And I will remind you this tomorrow. We don't have so many here with water ice. We have a lot here where complex organics happen. We'll remind this to you tomorrow. And not so many real here with methane and methanol. This is the region for silicates, you see? So this was giving us hopes on what we would find. And then this is the last one, where I show some of the, well, where I show nothing because this went crazy. But yeah, these were some science questions that I draw years ago, like in 4 or 5 years ago, that things that we wanted to answer. And we will go tomorrow when I show disco, spectra, and everything, we will see how far we go with them.
So thank you, Noemi. So have time for questions.
Noemi, you can put the slide of the size, albedo, and color that you, please. Yes. In this slide, I can see that Haumea, Makemake, and Aries have a high albedo. This behavior is because for the presence of methane, is for this.
Yeah, that is what we always thought, and that is what the spectra in the visible infrared shows us. When you have the ices have very high albedo. Silicates have lower albedos. As soon as you mix them with the ices, the albedo comes down. But also the complex organics that are formed after the graduation of simple ices like the CO or the CO2, they also have lower albedo. So for these ones, we expect to have a mixture of water ice, silicates, complex organics. For these ones, when we observe them in visible and near infrared, we have Haumea with 92% of water ice, and we have these guys that have a lot of methane, and they are a little bit regular. So reflection is not so. So they are probably replenished with ice. Probably you have some kind of atmosphere that collides and refreshes the surface.
You believe that in the case of comet with the nucleus is small, it's possible that you have a similar behavior in terms of the geometrical albedo.
Not for this. We have very, very, very low albedos for the
Yeah.
nucleus of cometary nuclei, around 4%, so they will be like here. And that is because these objects, they don't approach the sun as the comets do, or as the centaurs do, you know?
Mhm.
And when these objects approach the sun, they have a lot of episodes of sublimation. So you have this crust of silicates that showed at the beginning how it forms, and the silicates lower the albedo of the surface. So when you really observe a cometary nuclei that is not active, you have a featureless, almost neutral spectrum with a very low albedo.
Mhm. Yeah.
I ask a question about this. Using this slide, why you have so big error bars for Humei and Makemake?
Because for Haumea, I think is because of it basically comes from the albedo. Probably because of the shape of the object is affecting the estimation of the albedo. I don't know. And Makemake, I think something that is also influencing is that the light curve of these bodies is not very picky, so you cannot really estimate well the shape of the body. So the error bars come really from Tierno-Sarcourt, and is based on their estimations of the thermal component.
In this body, you observe some type of coma or
For these objects,
yes.
not.
No.
But for example, for Makemake, when it was observed with Tierno-Sarcourt, they saw like a phenomenon no, it was with an occultation that indicated like there could be some kind of transient atmosphere just at one point. You know, there is a weird peak there, and we did some kind of estimation of how much of an atmosphere it could have, but it was very, 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 very low. And that is basically because these objects that are the ones that are volatile ice-rich, the ones that are more prone to have an atmosphere, they have also very extreme orbits. They orbit like 90 astronomical units and even larger. So they're typically at very low temperatures. We think that when they approach, they may develop this atmosphere, but then when they go far, this atmosphere would collapse on the surface again.
And the last one. It's possible to identify, to say that the water ice is amorphous or crystalline in the spectrum, because it's
in the spectrum for water ice, we can say that. And for example, for nitrogen, we could even distinguish between two phases that it has at different temperature, depending on how much ordered the molecule is. Then the bands are thinner, are narrower.
But the band is very small.
Some bands appear when it is crystalline, and even if it is crystalline, depending on how ordered it is, the bands are narrower or they are broadened up. Remember that the bands produce because of movements of the molecules, so if everything is very sorted out, it all oscillates in the same wavelength, so you have very narrow bands. If it is more disordered, then the weight of the different atoms on the streams of these arms is a little bit different, and it produces peaks, like a lot of peaks at different wavelengths, so you have broader bands. So for some materials you can distinguish that, not for all of them.
So, thank you. More questions?
Hi, Noemi. Excuse me, I'm not a, I'm still a person. But, So you have shown different ices with different compositions. So if you have, is this a hint of where the comets have formed with this?
Yeah, we think so. For example, for the cold population, that is the one that we said formed outside. The others formed in hotter regions. When we study them with colors, they all show very similar colors. They have very small sizes, and a lot of them are binaries. So they have a specific indications, hints, that they have a different composition from all the others. So that could mean that the objects that formed further had a different material available, and then the appearance today would be different. So to do that, you really to go through those spaces, through those pathways, you need to have a lot of data from objects on the different classes. And up to now, there is not so much surface composition known on TNOs. So we only were detecting colors and water ice, and that is something that does not tell you a lot, because water ice, there is water ice on all of them. So that was why DISCO and JWST is so powerful, because it's going to tell you about others, like CO, CO2, like methanol, like nitrogen, like ethane. And if you get enough population studied with very good signal to noise and resolution so that you can detect all of this, then you can start trying to do that. And I think it's what we are doing, and it's what I'm going to tell tomorrow.
Thank you. I have one question there.
Thanks. Just wondering about when you mentioned all the internal reflections to the grains and all, how are the observations coming from polarization? Do you have surveys and infrared doing this?
Well, for our objects, it's like polarization is not something that we want to think about. I mean, it would even complicate things more. So it does not affect you. But I know that it affects some materials when you study them in the laboratory. Like, for example, CO2. When you deposit your thin layer of CO2, and then you collect the light from some place to study the band. Depending where you collect it, CO2 is very sensitive to polarization. So if you are not careful with that, you can get different results, and because we are not thinking of polarization, we are not aware that particular shape is due to this particular polarization. So before now, when we didn't have so many bands, it was not important at all, but it's going to be more important now that we have more bands.
Noemi, thanks for the very nice lecture. I'm in doubt. So if I understood correctly, if you have a body with some water layer under the surface, so you have a magnetic field. Is that correct?
If you have liquid,
yes.
Below that you have a magnetic field.
Okay, so is this the case for Europa, Enceladus, and also
I
Titan,
think so.
for example?
But they have, I think for them, the first studies that told them that there would be something there, it was because of irregularities in the thermal conductivity. Because it's also different if it is all ice or if there is some water below. I'm not an expert on those bodies, but I think that was the first indication.
And is there any effect due to the interaction of the magnetic field of the planet with the satellite or something like that?
Well, that is studied in some of the icy moons of the giant planets. The icy moons like Enceladus or Europa or Iapetus, they have materials that are pretty similar to this. They evolve in a different irradiation region, and also they are affected by the magnetic field. So, for example, also when they move synchronized with the planet, it's like one side, one hemisphere can collect material because it goes in the front, and some other doesn't collect it, it's on the back. So all of this environment is studied a lot on the icy moons of the giant planets.
So more questions? Anyone? No? So let's thank Noemi again.
Thanks to you all, and thanks for the questions.